Python uses a global interpreter lock, commonly known as the GIL. Can you explain what the GIL is, why it exists, and what its practical implications are when writing concurrent Python programs?
Absolutely. The Global Interpreter Lock, or GL, is a mutex, a mutual exclusion lock, that protects access to Python objects. It prevents multiple native threads from executing Python bytecode simultaneously within a single process. The reason it exists goes back to CPython's memory management. CPython uses reference counting for garbage collection. Every Python object has a reference count, and when that count drops to 0, the memory is freed. The problem is that reference counting is not thread-safe on its own. Without the GIL, two threads could simultaneously modify a reference count, leading to race conditions, memory corruption, or premature deallocation of objects. The GIL was the pragmatic solution chosen to keep CPython's internals simple and fast for single-threaded programs. Now, the practical implication is significant. For CPU-bound tasks, things like number crunching, data processing, or image manipulation, using Python threads will not give you true parallelism. Only one thread can hold the GIL and execute at any given moment. To achieve real parallelism for CPU-bound work, you must use the multiprocessing module, which spawns separate processes, each with its own GIL and memory space. However, for I/O-bound tasks, such as network requests, file reads, or database queries, threads work quite well because the GIL is released while a thread is waiting on I/O. This is also why Asyncio is so effective. It handles thousands of concurrent I/O operations cooperatively without the overhead of threads at all.
Great answer. You mentioned Asyncio. Can you walk me through how Python's async and await keywords work under the hood and explain the difference between concurrency and parallelism in this context?
Sure. The async and await keywords are syntactic sugar built on top of Python's generator protocol and the event loop concept. When you define a function with async def, Python creates a coroutine object. A coroutine is not executed immediately. It's a pausable function. When you use the await keyword inside a coroutine, you're telling the event loop, I'm going to wait for this operation to complete. While I'm waiting, you can go run something else. The event loop is a continuous loop, implemented by libraries like Asyncio, that manages a queue of coroutines. It picks up a coroutine, runs it until it hits an await expression, suspends it, registers a callback for when the awaited operation completes, and then moves on to the next ready coroutine. This is cooperative multitasking. Tasks voluntarily yield control, as opposed to preemptive multitasking used by threads. Now, the critical distinction. Concurrency means multiple tasks are making progress over the same time period, but not necessarily at the exact same instant. Parallelism means multiple tasks are literally executing at the same physical moment on multiple CPU cores. Asyncio gives you concurrency, not parallelism. It is single-threaded and single-process. It shines for I/O-bound workloads where the bottleneck is waiting, for a network response, a database query, or a file system operation. For CPU-bound work, Asyncio provides no benefit whatsoever because there is no I/O wait to overlap. The event loop would be blocked the entire time a computation runs. For CPU-bound parallelism, you still need multiprocessing or a library like concurrent.futures with a process pool executor.
Perfect. Let's switch to memory management. Can you explain Python's memory management model in detail? How objects are allocated, how garbage collection works, and what circular references are, and how Python handles them?
Python's memory management happens at two levels. At the low level, CPython has its own memory allocator called pymalloc, which manages pools of memory in fixed-size blocks. This is more efficient than calling the system malloc directly for every small object. At the higher level, Python tracks object lifetimes using reference counting. Every object has an internal field called obrefsnit. When you assign an object to a variable, or add it to a list, or pass it to a function, the reference count increases. When a variable goes out of scope or is reassigned, or a container is modified, the count decreases. When the count hits 0, CPython immediately deallocates the object and reclaims its memory. This is deterministic and very fast for most cases. However, reference counting has a fundamental weakness: circular references. Imagine object A holds a reference to object B, and object B holds a reference back to object A. Even if nothing else in the program references either A or B, their reference counts will never reach 0 because they reference each other. This is a memory leak if left unhandled. To solve this, CPython includes a cyclic garbage collector implemented in the GC module. It runs periodically and uses a generational collection algorithm. Objects are grouped into 3 generations, 0, 1, and 2. Newly created objects start in generation 0. If they survive a garbage collection cycle, they're promoted to generation 1 and then generation 2. The garbage collector runs more frequently on generation 0, since short-lived objects are most common and less often on generation 2. It detects cycles by doing a graph traversal, finding groups of objects that are only reachable from each other and collecting them together. You can interact with it via the GC module, for example, calling gc.collect manually or temporarily disabling collection in performance-critical sections.
Excellent. Now let's talk about Python's data model. Can you explain what dunder methods are, how they power Python's operator overloading, and give me some practical examples of how you've used them in real code?
Dunder methods, short for double underscore methods, sometimes called magic methods, are a set of special methods defined in Python classes that allow objects to integrate with Python's built-in language features and operators. When you write something like a plus b, Python doesn't literally add a and b. It calls a .add of b. If that returns not implemented, Python then tries b.rad of a. This is the mechanism behind operator overloading. Let me give some concrete examples. The ochre, repr, and str methods control how an object is represented as a string. Repr should return an unambiguous developer-facing representation, ideally one that could be used to recreate the object. Or store is the human-readable version used by print. The len method lets an object respond to the built-in len function. The getItem and setItem methods let an object behave like a container, so your custom class can support bracket indexing syntax. The iter and next methods make an object iterable, enabling it to work in for loops and with list comprehensions. The enter and exit methods are what make the with statement work. They define context manager behavior, allowing you to set up and tear down resources reliably. In production code, I've used dunder methods extensively. For example, I built a custom vector class for a machine learning utility where I defined add, mul, and apps so that vector addition, scalar multiplication, and magnitude calculations looked like natural mathematical expressions in the code. I also implemented eq and hash together on data model classes, so instances could be correctly compared and stored in sets or used as dictionary keys.
Nice. Let's talk about decorators. Can you explain how Python decorators work from first principles and describe a real-world use case where you implemented a custom decorator?
Decorators in Python are fundamentally just functions that take another function as an argument and return a new function. They leverage the fact that in Python, functions are first-class objects. You can pass them around, assign them to variables, and return them from other functions. Let me walk through the mechanics. When you write the @ sign followed by a decorator name above a function definition, Python desugars this into calling the decorator with the function as its argument. So writing at my decorator above def my function is exactly equivalent to writing my function equals my decorator of my function after the definition. Inside the decorator, you typically define a wrapper function that adds behavior before or after calling the original function, and then you return that wrapper. One important detail: you should always use functools.wraps on your wrapper function, passing in the original function. This preserves the original function's metadata, its name, docstring, and signature, which is important for debugging, introspection, and tools like documentation generators. In real-world projects, decorators are everywhere. I've implemented a retry decorator for API calls that automatically retries a function call up to n times with exponential backoff when a network exception occurs. I've written a timing decorator that logs the execution duration of any function, which was invaluable for profiling. I've also built an authentication decorator for a Flask REST API that checked for a valid JWT token in the request headers before allowing the decorated view function to execute. And in data engineering, I use decorators to define data pipeline steps declaratively, where the decorator registered the function in a processing registry and attached metadata like expected input and output schemas.
Good. Let's go deeper on generators and iterators. What's the difference between an iterator and a generator in Python? How does the yield keyword work? And when would you choose a generator over returning a list?
An iterator is any object that implements the iterator protocol, meaning it has both a iter method that returns self and a next method that returns the next value or raises stop iteration when exhausted. A generator is a special, more convenient way to create iterators. Any function that contains a yield statement is a generator function. When you call a generator function, Python does not execute its body immediately. Instead, it returns a generator object. The body only executes when you call next on the generator object, and it runs until it hits a yield statement. At that point, it pauses. It suspends its entire local state, including local variables, the call stack, and where execution is, and returns the yielded value to the caller. When next is called again, execution resumes exactly where it left off. This pause and resume mechanism is the core power of generators. The yield from statement is a further enhancement. It lets one generator delegate to another, which is useful for composing generators or recursively traversing tree structures. The key practical advantage of generators over lists is memory efficiency. If you have a generator that produces 1 million numbers, only one number exists in memory at any given time. A list of 1 million numbers holds all of them simultaneously. This is critical when working with large files, database result sets, infinite sequences, or streaming data pipelines. For example, if you're reading a very large log file line by line to find matching entries, a generator-based approach processes one line at a time and never loads the whole file into memory. I'd choose a list when I need to access elements multiple times, or in random order, or when I need the length up front. I'd choose a generator when the data is large, sequential, or potentially infinite, and I only need to consume it once.
Good explanation. Let's talk about Python's object-oriented features. Can you explain the difference between class methods, static methods, and instance methods, and describe the method resolution order in the context of multiple inheritance?
Let me address both parts. First, the three method types. An instance method is the most common. It takes self as its first parameter, which refers to the specific instance it's called on. It can access and modify both instance state and class state. A class method is decorated with @class method. Its first parameter is celse, referring to the class itself, not an instance. You can call it on the class directly without creating an instance. The classic use case is alternative constructors. For example, a class method called fromJSON that parses a JSON string and returns a new instance, providing a cleaner API than overloading init. A static method is decorated with @static method. It receives neither self nor CLS. It's essentially a plain function that lives inside the class's namespace for organizational purposes. It can't access or modify class or instance state. Use it when a utility function is logically related to the class, but doesn't need any class-specific data. Now, for method resolution order, or MRO, in multiple inheritance. Python uses an algorithm called C3 linearization to determine the order in which base classes are searched when looking up a method or attribute. The MRO defines a consistent, predictable order that respects the inheritance hierarchy and avoids the classic diamond problem. The rule is, a class always appears before its parents, and if there are multiple parent classes, they're searched left to right as listed in the class definition. You can inspect a class's MRO by accessing its MRO attribute or calling MRO on it. This is why calling super in a chain of classes works correctly. It doesn't just call the direct parent, it follows the MRO, ensuring each class in the chain is called exactly once in the right order.
Let's shift to Python's exception handling. Can you explain the full exception handling model, including try, except, else, and finally, and talk about best practices for designing custom exception hierarchies in larger applications?
Python's exception model is built around the try block, which wraps code that might raise an exception. If an exception is raised inside the try block, Python immediately exits the block and looks for a matching except clause. You can have multiple except clauses to handle different exception types. Python checks them in order and executes the first one that matches. The match is based on instance checks, so a bare except base exception would catch everything, which is almost always wrong. The else clause runs only if the try block completed without raising any exception at all. It's semantically cleaner than putting success path code inside the try block, because it makes it clear which code you're expecting might fail versus which code runs after success. The finally clause always runs, regardless of whether an exception was raised, caught, or even if a return statement was hit. It's the right place for cleanup code, closing files, releasing locks, or disconnecting from databases. Now, for custom exception hierarchies in larger applications, the most important principle is to define your own base exception class that inherits from exception. For example, application error. Then all your application-specific exceptions inherit from that. This gives callers two choices: catch your specific exception types for fine-grained handling, or catch application error to handle any error from your module in one place. You should avoid raising generic exceptions like exception or runtime error from your own code. Always raise something specific and meaningful. Exception classes can carry additional attributes to provide structured context. For instance, a database connection error might carry the host, port, and original exception as attributes, which makes it much easier to log, handle, or display a useful error message without having to parse the string message. In a large system, I'd organize exceptions into modules grouped by domain: network errors, validation errors, storage errors, and document them clearly as part of the public API.
Excellent. One more area, Python performance. What are your go-to techniques for profiling and optimizing a Python application that's running too slowly? Can you walk me through your process from diagnosis to resolution?
My approach always follows one strict rule: measure first, optimize second. Optimizing without profiling is guesswork, and you'll almost certainly focus on the wrong thing. The first step is profiling. For CPU performance, I use cprofile, which is built into the standard library. You can run it from the command line or wrap specific sections of code. It gives you a breakdown of how much time was spent in each function: total time, cumulative time, and call count. I then use pstats to sort and analyze the output, or visualize it with tools like SnakeViz or PySpy for a flame graph view. For memory profiling, I use Memory Profiler or tracemalloc, the latter being built into Python since 3.4. Tracemalloc lets you take snapshots of memory allocations at different points and diff them to find what's growing. Once I've identified the bottleneck, the optimization strategy depends on the root cause. For algorithmic inefficiency, the most common real cause, the fix is simply a better algorithm or data structure. Switching from a list lookup to a set lookup drops a linear scan to a constant time operation. Using a dictionary instead of nested loops can eliminate redundant computation entirely. For tight numerical loops, I'd move to NumPy for vectorized operations, which replaces Python-level loops with highly optimized C code. If I need to speed up a specific function further, I'd consider Python to compile it to C extensions, or use Numba's just-in-time compilation with a single decorator. For I/O-bound bottlenecks, like many sequential HTTP requests or database queries, the solution is concurrency via asyncio or threading. And finally, caching is one of the highest leverage techniques available. Python's functools.lru cache can eliminate repeated expensive computations with a single line of code. In distributed systems, I'd layer in Redis for cross-process or cross-service caching. The key principle throughout is profile, identify the actual bottleneck, apply the targeted fix, then measure again to confirm the improvement.